that you hear people talk about a lot. And then we talk about some specific models here for premixed combustion. Here the Bramos-Libby model, that's a model, is kind of a classical model also. It helps a little bit in the understanding also. And so we'll talk about this. We will talk about the level set method, the G-equation method. This is something we talked about already in the context of laminar flames. And then we'll move on here to modeling non-premixed combustion. And yeah, I mentioned already, non-premixed combustion, the conserved scalar mixture fraction is very important. There are very often people use conserved scalar-based models. There are different variants of this, and we'll talk about some of this. And then we'll introduce the flamelet model for turbulent combustion. We talked about the flamelet equations already. And then maybe talk about some applications here also. Okay, so we had this in one of the previous lectures already. We can write a conserved scalar equation, making a few assumptions that some of these terms are not so important, or just neglecting them here just for the sake of making the notation here a little simpler, especially for the energy equation. Then we can write the species equation and the energy equation, temperature equation here in the same form. And then you see you have a diffusion term or heat conduction term here. And then you have these terms. And then you have the chemical source term. Okay? And so we can just look at an equation like this and keep in mind this could be any reactive scalar here. Okay, so there are two so we can derive these averaged equations. Then you will have the scalar flux again, is modeled with a gradient transport assumption. We said this earlier. Plug this in here, and you get an equation that's closed up to this point, but then you still have the chemical source term, which is not closed. And now we could say, what if we, just here do also, I mean, you could say it's an what if we express this here also just in terms of the mean values, okay? So if you have this chemical source term here is like this, you could say is something that is of that form. We just want to have an estimate for how large is the error we would make if you don't model this right, okay? And for that we can say, okay, the chemical source term has this form. It's an exponential minus E over RT, and it's multiplied here by either the fuel or the oxidizer, whatever the deficient species is, okay? So let's say you have a lean flame, then the fuel would be the deficient species, and the oxygen concentration is just very large, but the deficient species then, the mass fraction of fuel can be expressed then again with a coupling function as by the temperature, okay? So mass fraction of fuel, the mass fraction of fuel you have left, that is proportional to the difference between the adiabatic flame temperature and the local flame temperature. If you've consumed all the fuel, then the temperature goes to the adiabatic flame temperature, right? So well, that's just form we want to use. And then one way would be to say, okay, maybe the mean source term here, maybe I can just express that in terms of the mean quantity. So I say ST mean, this here, would then be equal to rho b times TB minus T mean exponential minus E over R T mean, okay? Neglecting all the correlations that you get because you have a nonlinear function. Okay, that's one thing. We want to see how wrong is this. Is this wrong at all? And to do this, we just introduce here this decomposition, in this equation. And then if you do that, it's like a Taylor expansion. We do a Taylor expansion here. Taylor expansion of this term is simple, is this. Taylor expansion of this here gives you two terms, number 1 and 2. The term number 1 here, you see, is just a function of the mean, and then the second term here has this fluctuation. And so if we plug this in here, this is what we get. Okay? And then I can write this again. I can write it as T minus T mean, and then I have an extra term. And this here is also a function only of the mean. and then it's multiplied here by an extra term. And this is shown here. So this here would be the term just evaluated with the mean quantities. Okay? And then because of the expansion, because of the correlations, I get this here also. Okay? So if this is equal to 1, then evaluating this with the mean would be great. It's very good. Now, what you see is that E over RT, that is, something like the Zeldovich number. That is on the order of 10 typically. These are just typical values. And the turbulence intensity, the ratio of the fluctuation over the mean, that's often called turbulence intensity. Turbulence intensity is something like, 1/10 or 30% or whatever, something like this, okay? And now if you evaluate this, so this E over RT is 10, let's say, times this, let's say, is 0.3, then this would be 3 exponential 3. That's already a large number. That's order 10, okay? So there's a factor of 10. If you say 0.1, then it's a factor of 2 or whatever, okay? So it's something, this here is something between 2 and 10. Can be very large. This one here, that's actually, you could say almost even worse, because TB minus T mean, that can be a small quantity. And if you look at here T, so if I divide this here by T mean, then the numerator is 0.1. I divide this here by T mean. If this here becomes small, then this term here can become very, very large. And so both of these, you see, both of these can cause a big error at the end of the day. Okay, so this is not, so just this simple analysis seems to indicate if you would just evaluate this with a mean, you would make a big error, okay? So here's an example also. We take the mass fraction equations here, Favre averaged mass fraction equations, and now we introduce, we don't need to do this, just stay here. And now let's just say we write this for isotropic turbulence. Isotropic turbulence, remember, we said that statistics are the same in all directions, but also in each point. So if I take a derivative of mean quantities, they should be 0. Okay? So you see these are all derivatives here of mean quantities. These are derivatives of mean quantities. These are derivatives of mean quantities. So for isotropic turbulence, all these terms are 0. And the equation is just dy dt is equal to m dot mean. Okay? So that's good. Now we can do a DNS here for isotropic turbulence. This is shown here. So what you have here is a turbulent background field, and then we put patches of fuel and air in this field. And then the color you see is the temperature. The line is stoichiometric mixture. So at stoichiometric mixture, the temperature is high, and then everything else is low. And then the more you burn, the more regions have high temperature, right? And so if I evaluate the mean temperature averaged over this whole thing, then as a function of time, it goes up, okay? Because you burn more and more stuff in this box. So this is the temperature averaged over this whole box as a function of time, and you see the black symbols, that's the result of the DNS, it goes up. Now if I take this here, if I take this and I evaluate this here just with a mean mass fraction, then this is what I get. Okay? The temperature doesn't go up at all. It doesn't really burn. And if I use a simple flamenet model to close this, which is something we'll talk about later, then you see it's actually quite accurate, even though it turns out there's some local extinction here in this box, which shouldn't be described correctly with this model, but the model is not so bad. Okay? So closure by mean values is just, it doesn't work. It's not good. Okay, so let's look at some of these more simple models. There are several ones. This is obviously is a window here in the graphical user interface. that you get when you use the fluent code. And I don't know the details of this, but you see here, there's a section here, turbulence chemistry interaction model, and there's laminar finite rate eddy dissipation, eddy dissipation concept. You know? So they sound all very similar, and you know, I mean, if you just look at this, you don't know much about it. It's really hard to see what the differences are. So here again, one needs to be educated to know what model to use for what. So we want to go through some of these. First one here is the eddy breakup model. That's not even here, but it's the basis for some of these. Eddy breakup model is introduced here by Spaulding, 71. That was for engine-type combustion, spark ignition engines, premix combustion, and the idea here is infinitely fast chemistry, which means basically I just need to heat up the reactants up to a certain temperature, and then chemistry is infinitely fast. So the idea here is that the mass burning rate is really governed by the heating process or by the mixing process. How does the turbulence mix the reacted gases with the unburned, and then of course the dissipation will take place and will mix also on the molecular level. And so that's the eddy breakup model. So the reaction rate of this is given here. So you say the turbulence does something. So I use the turbulent timescale. So this mixing comes by turbulence, so the timescale should come from the turbulence. Epsilon over k, that's a turbulence timescale. And then it should be proportional to some species here. And so this is the product mass fraction. Why is the product mass fraction here? Because actually it's the variance of this. So if there's no product, you can't preheat the unreacted mixture. So the idea here, basically, this looks very much like a dissipation rate. Remember the dissipation rate earlier for mixture fraction. We said we can model it by epsilon over k times the variance of mixture fraction. So this here looks very much like a dissipation rate for the product, or let's say for the hot gases. So what the turbulence does, it brings patches, as shown here, it brings patches of hot gas into the unburned, and then the dissipation of this variance that you form, that mixes the hot products with the fresh reactants, and so this preheats the reactants. And so this is kind of the idea that's behind this. Okay, so use this. Was that a question? Yeah.
I have a question. At time t is equal to 0, I don't have any product.
Yes.
So how does it work?
Well, I mean, in this, if you take a bottle of fuel mixed with air, okay, and at time 0 you have no product. What happens with the fuel and air? It doesn't burn.
Yeah, but so
that's the same here.
How does it ignite?
How do you ignite in an engine?
By heating it with a spark.
With a spark.
Yeah.
Same here. So initially you would set, what does the spark do? It creates products. Yeah. So initially you would set some product somewhere.
So you have to initialize the simulation with some product.
Well, you have to initiate the combustion process with a spark. Yeah. How does a spark model look like? Basically, a spark model would give you some region that now is hot. Hot in this context would mean you have reaction products. Yeah. So, I mean, so there are issues with this model. Issue with the model is that this doesn't know anything about chemistry. You see that? This doesn't know it's lean or rich. And so this doesn't know if you have EGR. So we know, for example, EGR doesn't burn that fast. This model doesn't know it. For example, if you want to apply this to non-premix combustion, then, I mean, the whole thing wouldn't work really. Lean-rich combustion, it doesn't do this. So there's another model here by Magnussen. It's called the Magnussen model, or it's also called the eddy dissipation model, that tries to take care of this. Try to formulate the same thing for diesel engine combustion. Okay? So if you formulate for diesel engines, you would say, okay, again, assumption is if the combustion is very, very fast, and then you would say, here mixing is dominant time scale, so again I have a turbulent time scale here in my reaction rate. But then what they do is they say there are regions where, so this again should be proportional to some species, and they say, oh, well, in a diesel engine I have rich regions where I have no oxygen or very little oxygen, and I have lean regions where I have very little fuel, and always the deficient species, that is the most important one, okay? So what they say here is you have this E is educt, so this would be the reactants, this is the product. So you evaluate this with the reactants, you evaluate it with the product, you evaluate it with the, right, so you evaluate it with just the fuel, okay? You evaluate this just with the oxygen, and you evaluate it with the product. So the idea is, if you have no fuel, you won't have heat release. If you have no oxygen, you won't have heat release. And if there's no product, same thing, then it can't ignite, you don't have heat release. And so you take now always this, you evaluate all three, and you take the smallest one of these, and that gives you the reaction rate. Okay? Now, same question again, how would it ignite? In a diesel engine, you do actually have auto ignition, there's no spark. Here, you have to use a ignition model first. There's a model that does nothing else than predict now is ignition, and then you have to initialize it somehow. Here again, you need to put some product somewhere, and then this model keeps going. Okay? So you see here you have this B parameter, A parameter. So these are two parameters. That's not so good, because if you have one parameter, you can always fit it to some experiment. You have two parameters. That's not so easy. Fit, it's two-dimensional space. You have to fit parameters. But that's what people do. So typically, if this model is used, what you would do is you have an experiment. You do many simulations. You fit these constants to match the simulation, and then you say, okay, now the model is good. Now I can do parameter variations. Maybe you change the speed, or you change whatever you want to change, the geometry of the engine a little bit, and say, okay, model is probably still good. But the matter of the fact is, these constants, they need to be fitted. Every single time you look at a different case. Okay, so this we just talked about. I mean, you just evaluate this for fuel, for oxygen, and so on, and you always take the smallest one. So, summary here: this is controlled by mixing. You assume fast chemistry. It can be used for premixed and non-premixed combustion, and it also knows something about rich or lean to some degree. It can give you full or partial conversion. If things don't mix, they just wouldn't burn. And the advantage here is simple, robust. The disadvantage, of course, you need to do this fitting. It doesn't know anything about non-equilibrium. So, for example, NO or local extinction wouldn't be described by this. And if you have regions where finite chemistry here, for example, NO formation is important, then fuel consumption would be over-predicted because you assume fast chemistry. So, for example, what you see is that the pressure trace usually is not predicted all that well, or you look at the heat release, because in real combustion you first form CO, and then CO gives products, and here is basically is a one-step type of reaction where as soon as the fuel is consumed, you would form products. Okay, so this was the suite of these mixed is burned models, basically. And so then another common approach, because it's seemingly simple, it's expensive but simple, and it's seemingly you can apply to non-premixed, premixed combustion. You don't need to choose a combustion model. And that is what just 10 minutes ago we said doesn't work. So this is what's called here finite rate chemistry model, or some people call it laminar chemistry model. But basically it means you take the chemical source term and you just close it with a mean. Okay? So you solve an equation for each species. So you know all the yi's, the yi means, and then you know the mean temperature, and you just close everything with a mean. That's what we just said is not good, but that's what some people use. So this would be good for if you have a totally homogeneous system or laminar, but for turbulent case, actually, as we just saw, it shouldn't work. So this gives you a solution that's chemistry controlled. It doesn't know very much about mixing. Maybe that could be applicable if the chemical timescale is very, very large compared to the mixing timescale. Maybe then it's not so bad. And it seems like you can apply it for anything, but one has to be careful. Source term here is a Arrhenius source term, and it has potential to model non-equilibrium effects, but maybe not too accurately. Okay, so we talked about this eddy dissipation model, and we talked about finite rate chemistry. And maybe you could combine these. Maybe you could say, well, the one is right if the chemistry is infinitely fast and mixing is slow, then it's not so bad. And the other one is right if mixing is infinitely fast and chemistry is slow. Okay, and so here, same thing. You have a reaction rate. You get a reaction rate from the fast chemistry model and one from the fast mixing model, and you take the smaller one of the two, and that gives you your reaction rate. Okay, it's a little empirical, but in these two limits then, either where the chemistry is really infinitely fast or mixing is infinitely fast, in these two limits, the model should be good. So the advantage, the model is meant for a large range of applicability, and the disadvantage, of course, it has no turbulence chemistry. It doesn't consider really turbulence chemistry interaction. Okay, so the problem with this also is that you need to solve these equations. If you have a chemical mechanism with 50 species, then you would need to solve 50 transport equations in your CFD code, and that is very expensive. And then also these chemical source terms, they need to be evaluated, and that is very, very expensive. Evaluating these source terms, they're all nonlinear terms, and it's quite expensive. So another one is this eddy dissipation concept that now also tries to bring in the chemistry, but also some mixing, a time scale. So there is it's also a little empirical. You have this xi. Where is the xi? Here. You have this xi value, which is maybe this should give you a volume of the small scale. So you see this is built here with small scale quantities, nu and epsilon. This should give you the volume of the small scales. And then you have a time scale here also. The time scale of the reactions should be, this is also a small scale quantity here. This is a constant which is specified here in this code. And then the source term here is given by this, so it depends here somehow on these small scale parameters. And then this here is just an expected value from the chemistry that you would get, and this here is your current value. So you see this here is what it is basically is a relaxation process of your current value to a chemically determined value that goes somehow here with a small scale mixing time scale. So I don't want to make an argument for or against any of the assumptions that go into how this is put together or whatever. This is just what it is. This is a model also that some people use because, again, seemingly it gives you these finite rate chemistry effects, but it also gives you some of the turbulence. But again, the model is quite expensive because, again, you need to you need to solve these equations for each single species, and the numerical integration of this, apparently, from what I hear, is quite expensive. So whenever people come to us and they want chemical mechanisms, they say, we use this eddy dissipation concept. Could you give us a chemical mechanism with only 3 species or whatever? And so it seems quite expensive. There is this ISAT algorithm. This is a method that was developed by Steve Pope to speed up the integration. It's a tabulation method, basically, where before you integrate from time step chemical source term from time step n to n plus 1, you see what's my composition. Then you go in your ISAT table and you see, did I ever compute this composition? If yes, then you know what the result is, and so that's how you do the. And if not, then you do the calculation, using a stiff ODE integrator, but then you store that solution in your table. And the next time you come across the same composition, then you can just get your solution from this ISAT table. So there's a way to speed this up, and this apparently used here also, or maybe you can use this here in Fluent. Okay, so maybe here, to summarize, there is this laminar finite rate chemistry model where you only solve the Arrhenius terms with a mean. That is good for infinitely fast mixing, very slow chemistry, but maybe not otherwise for typical combustion processes. And then you have this combination here of the finite rate and eddy dissipation concept, where you calculate Arrhenius rate coefficients and the mixing rate, and then there's a local choice which one is the smaller one, and you either take the mixing controlled or the chemistry controlled rate, and then there's the eddy dissipation concept, which is just mixing controlled, and then there's the eddy dissipation model, and there's the eddy dissipation concept. Which is the one I just mentioned that creates these volumes for the small scales and time scales for the small scales and so on. Okay, so as I mentioned, maybe we have 3 more minutes, and we should just go over this chapter here real quick. There's some material here on how PDFs are defined, joints that join PDFs, conditional PDFs, and all of that. And we shouldn't go through the details of this. This is mostly follows here the turbulence book here by Professor Pope, and it just summarizes some of these things. Sample space. What's the difference between a random variable and a sample space variable? How can you define just with events? How can you define a probability? Basically, you first need to define an event. Event means something that's true or false. And if you define something true or false, you can also define a probability. How often is something true or false? A coin toss, right, is either 1 or 0, and then you define a probability, how often it's 1 or 0. That's a probability, and then the question is, how can you define probabilities in terms of velocities? Because if you do a velocity measurement, it might be 5 meters per second, but it's not true or false. And so you have to define yourself an event that you can measure as true or false. And the event we define is we take we prescribe a velocity, let's say 10 meters per second, and we just look at how often is the velocity smaller than that value. Okay, that's true or false. It's 5 meters per second, it's smaller. It's 5,500 meters per second, then it's larger. Okay, it doesn't measure how much larger, it just says true or false. And then I can get a probability of this. Once I have a probability, I can, you can also define joint probability by saying, by measuring the velocity, or let's say a u velocity and the v velocity, and looking at these at the same time. Once you have these probabilities, you can define what's called the cumulative distribution function, which is just a probability for for arbitrary values of this fixed velocity. And from this you can define PDFs, the probability density function. Most of you probably know or have an inherent understanding of what a PDF is. If you want to see how it can be defined rigorously, is shown here. This is a 10-mark bill. This is out of service now because we use euros in Germany, but this used to have a Gauss here, and the Gauss function used to be on this thing. So in the math exam, if you didn't know that, you just look at your... Nobody can say you can't carry money with you. There are some others here, delta function, double delta function. If some of these are unknown to you, maybe you want to look at this. Moments of a distribution, and then here joint PDFs, and so on. And then finally, joint PDF. If you joint PDF, it gives you the probability density of two events. So how likely are these two events to occur at the same time? And then you can also define so-called conditional PDFs, where you say, let's fix one value, what is then the PDF of the other value? And the conditional PDFs and the joint PDFs, they can be converted into each other by the so-called Bayes theorem, which is given here. So once you have the conditional PDF and the PDF of one of these species, one of the variables, then you can also get the joint PDF or vice versa. So you should always think of joint PDF and conditional PDF as something very, very similar. Okay, so that was just... so if any of this is, you're not comfortable with this, maybe you want to use the evening or the late afternoon, definitely not the next 2 hours, to look up on this. And so we close now. Again...